In this video, we discuss learning outcome number 1, which is all about computing and interpreting z-scores. A z-score, also known as a standard score or a standardized value, is a number of standard deviations that a given value x is above or below the mean. So we're trying to compare that data value that we have to the mean. One way of doing that is by looking at this z-score. The way we compute a z-score is to use one of the following formulas. If we have the sample mean and the sample standard deviation, we're going to use the formula on the left. If we have the population mean or the population standard deviation, we'll use the formula on the right. And our round-off rule for z-scores is to round to 2 decimal places because that's what we see in the table of z-scores in the back of the book. Historically, I believe the tables have always included z-scores rounded out to 2 decimal places. So that's what we'll do when we're computing z-scores. So here are some important properties of z-scores. The first is that definition. Again, it's very important that we know how to interpret these numbers. You're going to calculate them using those formulas, which are very simple, but most importantly, you need to know that the z-score is the number of standard deviations that a given x value is above or below the mean. It's a count of standard deviations. Because it's a count, it's just a number with no units of measurement. If we look at that numerator and the expression for z-scores, you're taking a data value and you're subtracting the mean. So let's say that the data values are measured in minutes. Well, if you take minutes, that would be your data value, and you subtract the mean, which is also in minutes, you'll still have minutes. So you're getting that deviation from the mean in minutes. And then if I want the number of standard deviations, so if I want the corresponding z-score, I take the deviation that I have and I divide by the standard deviation. And that's going to tell me how many standard deviations I am above or below the mean. So I'll have minutes in the numerator. The standard deviation in the denominator would also be in minutes, and the minutes over minutes cancel, and we just end up with a count or a number of standard deviations. So these z-scores have no units of measurement, so all the units of measurement cancel out, and you're left with just a number of standard deviations. Now we're going to say that a data value is significantly high or significantly low if that data value is more than 2 standard deviations away from the mean. And we said that before, we said that in lesson 3.2, but now we're thinking of numbers of standard deviations differently. Instead of just counting standard deviations, we can take that data value, and assign it a corresponding z-score using the formulas that we looked at on the last slide. So we said before that a data value is significantly high or low if it's more than 2 standard deviations away from the mean. Well, if a z-score is a measure of the number of standard deviations, we'll say that that data value is significantly low if its z-score is less than or equal to -2. Because remember what z equals -2 means. That means the data value is 2 standard deviations below the mean. If z is less than -2, that means the data value is more than 2 standard deviations below the mean, and it's below the mean because that z value is negative. We'll say that the data value is significantly high if it's if the z-score is greater than or equal to 2, because z equals 2 means that the data value is exactly 2 standard deviations above the mean, and if z is greater than 2, well, that means that that data value is more than 2 standard deviations above the mean. So we would say it's significantly high. And then this is related to what I was just talking about. If that value is less than the mean, the z-score is negative. If the value is greater than the mean, the z-score is positive. If a z-score is equal to 0, the number of standard deviations from the mean is 0. That means that we're talking about the mean itself. So the standard deviation for the mean, or the number of standard deviations that a given value is above or below the mean, is the z-score. So z positive means it's above the mean, z negative means it's below the mean, z equals 0 means that the data value we're looking at actually is the mean. So here is an example. We're going to pair some values using their z-scores. This is exercise 15 from section 3.3 of our text. It says newborn males have weights with a mean of 3,273.8 grams and a standard deviation of 660.2 grams. And newborn females have weights with a mean of 3,037.1 grams and a standard deviation of 706.3 grams. The question says, who has the weight that is more extreme relative to the group from which they came? A male who weighs 1,500 grams or a female who weighs 1,500 grams? Now, first of all, let's think about these numbers and what they mean. If you have a baby that weighs 1,500 grams, well, clearly that is much less than the mean in both cases. This is a very underweight baby. If we have a newborn male and the mean weight of newborn male babies is 3,273.8 grams. This 1,500 grams, is less than half of that. And the same is true for the newborn female with a weight of 500 grams. It's actually a mass, but we won't get into that. If that female weighs 1,500 grams, well, that's less than half of that 3,037.1 grams as well. So these babies are very underweight. You should also notice that the standard deviation for males is 660 grams, and that standard deviation for the female weights is 706 grams approximately. So that means that the female babies have weights that vary more because the standard deviation is greater. The female babies have have weights that vary more than the weights of the male babies because the standard deviation of the females is greater than the standard deviation of the males. So let's answer this question. Who has the weight that is more extreme relative to the group from which they came? Well, in order to do that, we'll just calculate a couple of z-scores. For the newborn male, we're going to take that 1,500 grams and then we'll subtract the mean for male newborns. And then we'll divide by the standard deviation for male newborns. So you have 1,500 minus 3,273.8. That's going to give you a deviation. And then you'll divide by that 660.2. And we get negative 2.69. And remember how you want to interpret this. That means that that newborn male baby is 2.69 standard deviations below the mean. Do the same thing for the females. You just use the mean weight for female babies and the mean or the standard deviation for female babies when you calculate this z-score. So you do exactly the same thing. You subtract the mean from the score and then you divide by the standard deviation and you get negative 2.18. So that means that the 1,500 gram female newborn, is 2.18 standard deviations below the mean. So when you're talking about whether something is more extreme, you're saying, how different is it from the mean? So we're not really even interested in these signs. The fact that both of these are negative just tells us that the baby is underweight rather than overweight compared to the mean. But we're really looking at and interested in the absolute value of that z-score when we're thinking about whether a value is more extreme. So when we're answering this question, we can say that since the absolute value of the z-score for the males, that was 2.69 standard deviations, is greater than the absolute value of the z-score for the females, which was 2.18 standard deviations below the mean. Since that's true, we'll say that the male baby's weight is much more extreme. Okay, now we can also use our z-scores to identify significant values. Now, this is just the range rule of thumb. We said before when we were using the range rule of thumb that if a value was more than 2 standard deviations above the mean or less than 2 standard deviations, not less than, or more than 2 standard deviations, below the mean, then that value is significant. We're just going to take that same rule and translate it into z-scores. So significant values are those with z less than or equal to negative 2, which means that that corresponding data value is either 2 standard deviations below the mean or more than 2 standard deviations below the mean. Or z is greater than or equal to 2, which means that the corresponding data value is 2 standard deviations above the mean or more than 2 standard deviations above the mean. And we've got this graph again. It looks pretty much the same as before, just our tick marks are a little different now. These tick marks now represent z-scores, and remember, z-scores are numbers of standard deviations above and below the mean. So at the mean, we've got a z-score of 0. If you are plus or minus 1 standard deviation from the mean, we'll say that's not too significant. That's sort of typical. That's okay. If we are within plus or minus 2 standard deviations from the mean, we'll say that's sort of typical. But if a z-score is greater than 2, then that value, the corresponding value, is significantly high, because that means the corresponding value is more than 2, or excuse me, is greater than or equal to 2 standard deviations above the mean. Now, if the z-score is to the left of this -2, that means that the corresponding data value is more than 2 standard deviations below the mean. So here is an example dealing with SAT scores. It says scores on the SAT have a mean of approximately 500 and a standard deviation of approximately 100. Compute the z-score for a score of 720. Is 720 significantly high? First, we compute the z-score. So we take our 720 and we subtract the mean of 500, and then we divide by 100. So we've got 220 divided by 100, which gives us 2.2. Since that z value is more than 2, that means that the score of 720 is significantly high. But again, remember how we want to interpret that 2.2. That 2.2 tells us that that score of 720 is 2.2 standard deviations above the mean. Since it's 2.2 standard deviations above the mean, we say that the score is significantly high. And that's it for this video. I'll see you in the next one when we'll talk about learning outcome number 2.